Dragomir Radev is the A. Bartlett Giamatti Professor of Computer Science at Yale University. He leads the Natural Language Processing Lab at Yale University. His research focuses on computational models for natural language understanding and generation, as well as their applications. He is one of the co-founders of the North American Computational Linguistics Open Competition. He is fellow of ACM, AAAI, AAAS, and ACL. Today, he will be presenting his talk on closing the loop in natural language interfaces to databases, parsing, dialogue, and generation. Over to you, Drag.
Hi, everybody. Can I please ask you to check if there's some noise coming from somewhere, the background noise?
It might be from my side.
Thank you so much. Appreciate that. Okay, so let me share my screen, make sure everything is okay. Can you see my screen?
Yes.
Okay, very good, very good. So I'm going to start in just 1 second. Okay, so can everybody hear me okay?
Yeah,
Yes.
all fine.
Okay, very good. Thank you so much for inviting me. I was very happy to be able to attend some of the presentations so far, and I can say that this is a very nice workshop with a lot of very interesting people saying very interesting things. So as you just heard, I am a professor at Yale University, and I lead here the Language Information and Learning Lab, which is this Lily. If you're interested in our other papers and other work, you can always go to our website. We have a lot of interesting demos, and in particular, a lot of data sets and software on GitHub. I will mention some of it in today's presentation, but there's a lot more that may be of interest to different groups of you. So what I'm going to talk about today is how we use natural language processing to close the loop in natural language interfaces to relational databases. And this is joint work with a large number of people, and I would particularly want to cite 3 of them. Those are PhD students in our lab. 2 of them recently finished their PhDs, and 1 is still here, and also a lot of our collaborators from industry and from other universities. Okay, so what am I going to talk about today? Natural language interfaces to structured data. So as you know, we have data in many different forms, many different genres. So that can be anything from very structured data like databases. It can also be in the form of knowledge graphs. It can be web pages and tables, which are a little bit less structured. They contain a lot of free text. And then finally, it can be something completely unstructured like text and images and videos. There has been a lot of interesting work in NLP for each of those different genres of text. Today, I'm going to focus more on the things on the left, so the first 3 of those, and I'm going to show you how we have designed several systems and several interesting data sets that can handle interesting problems for each of those 3 types of data. So very quickly, what is a natural language interface to a relational database? What you see here are SQL or SQL statements that give you answers for many different questions. Of course, we don't expect our users to understand SQL to be able to ask questions like this. So instead, what we want to do is to make sure that everybody should be able to talk to the database in their natural language. So instead of giving the SQL query, they should be able to say, how many units of this particular item are available in stock. So the text to SQL problem is about translating natural language sentences with or without context, maybe or not part of a dialogue, using some sort of a database as the backend, and then combining those 2 to form queries that can be executed on the database, and then possibly returning the results back to the user either in the form of a table or in natural language. So this is the main point of today's talk. So I'm going to discuss how we do understand the user. So that includes things like semantic parsing and text to SQL processing. In particular, I'm going to focus on our paper from 2018 on the Spider dataset. Then we're going to talk about understanding the data. So we have done some interesting work on language modeling for tables, so specifically training on tables and the text surrounding them. And then finally, in order to close the loop, we're going to talk a little bit about structure to text or data to text generation, and also question answering and summarization over tables. So all of this together allows us to have some sort of a closed loop, which can be exploited in a dialogue setting. Okay, so let me show you first why table semantic parsing and text to SQL is a challenging problem. Suppose that we have a database that consists of those three tables. So one is about tennis matches, one is about ranking of players, and the final one is about the players themselves. So suppose that the user asks a question like this one: which European countries have some players who won the Australian Open at least 3 times? Now, in order to answer this question, you have to do at least 2 things. One is to understand the meaning of this sentence, which is typically done using semantic parsing. And then second, you have to execute this query on the database and then return the results. So the semantic parser does the first part. It will look at the table and then convert this user question into a valid SQL statement that can be executed. And if something is unclear, if it needs more context, or if there's some sort of an error, then it should be able to go back to the user and ask some follow-up questions. So once you have this query, you have to execute it on this data set. But even before then, you still have to worry about a lot of little things which make the whole process fairly complicated and hard to solve. So, for example, in order to get this answer here, Switzerland, you have to be able to combine information from each of those tables using database joins and other operators. So one of those things requires you to understand what are the meanings of the cells in the table. So for example, you need to know that Australian Open refers to the name of a tourney, a match, a tournament. European here refers to another value of the cell, which is the location of the different tournaments. Another piece of the input text, like countries and won in this case, map to column names like winner ID and nation in this particular case. Then in blue, you also have table names. So the word player here is not associated with any particular cell or row or column of those tables, but rather associated with the entire table. And then finally, you also have some logic snippets, which are also interesting and very important to parse properly. So in this case, this purple text here, at least 3 times, will have to be converted into this SQL code here, group by, winner ID, and then you want to make sure that the count in each of those categories for each of the winners' IDs is greater than or equal to 3. So now I'm going to introduce our first paper in this sequence. Sorry. So this is a paper from EMNLP 2018, which started our project. And the first author of this paper is Tao Yu, whose PhD was on the topic of semantic parsing for databases. So Spider is currently the largest and most popular data set for text to SQL that involves multiple tables. It was created over multiple months by more than 10 graduate students in our lab, and it contains 10,000 questions in natural language, which were created from scratch, not through any automatic grammar or generation. Those correspond to 6,000 unique SQL queries and also 200 different databases. So unlike previous data sets, we were able to cover a fairly wide range of databases in many different domains, in this case, 138. So one interesting property of this data set is that it has a large number of what we call complex questions. And those complex questions have the following database correspondences. So one of them is that they contain multiple tables with foreign keys and are joined together. And then you also have aggregate commands in SQL, for example, minimum, maximum, and average, group by, having, and so on. And finally, we also have a lot of questions that have nested queries, like the examples on the previous slide. So this data set is available on our website. I'll show you some links at the end. And we have a leaderboard where people can submit their results on the development test. And we can also secretly score them on the test set, which is not publicly available. So as you can see, this was a fairly large task to build this data set. The total amount spent was about 1,000 hours, but it paid off because this data set has been extremely helpful, not just for our own research, but as you will see, for many other people's research. So this annotation process involves several steps. For example, we had to collect databases first, then we had to build the questions, write SQL annotations. We also had to review the SQL statement. So the person different from the person who wrote the SQL statement verified that this is correct. We also made sure that they can be executed properly on the database itself. We also did some paraphrasing in order to augment the data set from about 8,000 to for more than 11,000. So we have about 3,000 additional paraphrases of existing questions. And then we also did a lot of additional final review of all the SQLs and for consistency and for diversity of question types and so on. So each of those things took a lot of time. As you can see, some of those took 500 person hours, 150 person hours, and so on. So the quality control was done also over a fairly long period of time. We looked in particular for things like SQL pattern coverage, make sure that we cover all the different SQL statements that we're interested in, and that each of the tables in the database appears in at least one query, that we have a certain percentage of nested queries, that if there are multiple equivalent SQL queries, that we cover all of them as much as possible, and that also the natural language questions are as clear as possible and as natural as possible. So when we published this data set, which again was about 3 years ago, it was, and it still is, the largest data set for multi-table databases. As you can see, it has a smaller number of questions and SQL queries than compared to WikiSQL, which was an earlier data set created by Salesforce and some other institutions. But we are the first one to have a very large number of databases with multiple tables and all of those different special statements. So one of the things that we did with this data set is to split the questions into 4 different categories based on complexity or hardness. So some of them were easy, like this one here. Then we have medium, hard, and very hard. And then when we report results on this work, we always group the performance in each of those 4 different categories in order to understand whether a particular new method is more appropriate for very simple queries, or maybe it gives us some additional mileage for the really hard ones, like the ones that have nested queries and aggregate statements. So as part of this project, we also built a couple of different systems. One is called TypeSQL, and one of them is called Syntax SQLnet. Both of those were published in 2018. In both of them, we looked at different ways in which we can transform the natural language questions into parse trees, and then from parse trees to SQL commands. So here's an interesting slide. I just pulled this a few hours ago from the Spider leaderboard. As you can see here, when we started this project, we were getting a very low performance. So on the dev set, something like 8%, 10%, and then the test set about the same performance. And then over the years, we have received a large number of submissions, and the performance has gone up, slowly over the years, from 10%, 36%, and so on, until a couple of months ago when we now have performance that is in the 70s. So fairly large number of participants here. Some of those are still anonymous because the papers haven't been published, but as soon as the paper gets published, we update the leaderboard and we de-anonymize those entries. So this data set is available on the Spider website, and you can download the code and also the data from there. So Spider, as I mentioned before, has been very popular. It was one of the shared tasks at the workshop on interactive and executable semantic parsing last year at the MNOP 2020, which also involved a large number of participants and a large number of invited speakers. It was translated in several other languages, starting with Chinese in 2019. And it has become very popular. We've had more than 100 submissions from top research labs, pretty much most of the main players in this field in the last 3 years. And then finally, it has also led to about 40 publications in the top AI, machine learning, NLP, and database conferences like iClear, AAAI, VLDB, and so on. So one thing that a little bit relates to what Monojit was saying a little bit earlier is that there's a big gap in performance over the years from the so-called Word2Vec era up until around 2018 and then some early 2019 papers. So you can see the performance here is very low, less than 50% set match accuracy. And then once BERT became popular, we had a big jump throughout all the participants, including our submissions and also other people's submissions. So this one is one of ours, this one is one of ours at the beginning, this one, and also this one here, which use different sorts of transformers. Okay, so once we finished working with Spider and we popularized it, we started discussing different ways in which we can enhance it so that we can have a dialogue system and also to generate output in natural language from the query results. So the first data set that we created after Spider was called SParC, which is about dialogue versions of SQL. So for example, we have here a database and the user asks questions like find the names of the students who live in a dorm that have TV lounges. And then this is converted into a SQL query. And then the user is allowed to ask additional questions, which then can be answered in SQL format in the context of the previous questions. So we have created a set of dialogues of this sort where each additional SQL query has to be evaluated separately from the history so far. So here's an example of our data sizes. So SParC was compared to the existing data sets. As you can see, there's a big improvement here in terms of the coverage. So we have context, just like some of the other data sets here, but this is all based on databases. And it is also cross-domain, which is what the previous systems did not have in this domain. And then in terms of size, it is also fairly large. It has 4,000 sequences over 200 databases compared to just one domain in the very classic, very old 80s data set in airline reservation. So SParC, just like Spider, includes a lot of different SQL syntactic statements. So for example, it has a large number of aggregate commands and also nested queries. It is also cross-domain. So we have 140 databases for training, 20 for development, and 40 for testing. So this is the leaderboard for SParC. As you can see, we keep getting very good submissions. The performance has gone up just over the last year and a half from 48% to 65% on the question match evaluation. We also have a website where you can download the code and the data. And again, we have some statistics that compare CoSQL with some of the other data sets, which are used in this particular case for dialogue state tracking, like the DSTC challenges and the multi-was challenges. Okay, so I'm going to skip a few slides here, and I'm going to switch to the third data set that we created, and this is called the CoSQL data set. So this is about SQL-grounded dialogue state tracking, which was also released in 2019, and it also has been very actively developed over the years. We went here from a performance very low, less than 15% to 53% over a year and a half. Okay, now I'm going to switch gears a little bit, and I'm going to talk about understanding the contents of the table without the context of user questions. In particular, I'm going to talk about a system called GraPPa, which was published recently a few months ago in ICLR 2021. And this system is about grammar augmented pre-training for table semantic parsing. Or in other words, we are training a language model that specifically understands the content of tables. And by content of tables, I mean both the metadata, for example, the parts of the schema, such as types of the data types, the column headers, the number of rows in the table, and so on, the table title, but also the data itself. So this is trained on tables that don't just have a schema, but they also have actual data records in them. So let me explain how we do this. So traditional language models such as BERT and RoBERT and most of the others have been extremely successful in many different natural language processing tasks. Everybody has been talking about this in the previous presentation. So GLUE came up earlier today. So most of the performers in the last 2 years have been using different variants of those pre-trained language models to get the highest performance, which in some cases is even higher than human performance. However, most of those language models are trained on text. So for example, Wikipedia articles, again, not structured data, just plain sentences. A lot of them are trained on books, including the original BERT model and many others. Now, in table semantic parsing, we also need to be able to encode the tables and to jointly understand the questions on the tables and also figure out some logic operations. Like in our case, it was at least 3 times. So in order to do this, we have to train the model not just on plain text, but also on the table and their context. So there has been work on this before us. There are 2 papers from 2020 that I would like to cite by Yin et al. And Herzig et al., which train language models on millions of text table examples extracted from the web. Those are very noisy examples because they have the table, let's say from a Wikipedia page, and then the surrounding sentences, which may or may not match the contents of that table exactly. They may be about some other table, or they may even be not included in the tables at all. So here's an example of the data that is used to train those models. So you have a table from Wikipedia, and then you also have the surrounding text, like median age of the population. As you can see from this example, there is some interesting overlap between the contents of the table and the surrounding text, but most of the overlap is not there. You really don't have enough information in the text surrounding the table to describe the contents. So this is one of the challenges that we have to address. Here's one more example of this. So this is very noisy, as I mentioned, and it's not ideal. So one of the things that we tried to do first was to do some data augmentation. Everybody knows what data augmentation is. It has been used in a lot of papers in the past. For example, Zhang and Liang used a synchronous context-free grammar to create recombinant examples. There's been also earlier work and also more recent work on this kind of data augmentation. And then in another piece of work, we have people like Herzig and Brandt and Andreas Campagna and so on, which also created this kind of augmentation using the table specifically. Well, it turned out that even though we were expecting to get higher improvement of the performance using this kind of data augmentation, we actually did not get any additional performance improvement. So when we evaluated the model on Spider, SParC, and CoSQL, we actually saw that the performance with synthetic training data is about the same, and on Spider, in like 4% lower than without the synthetic training data. And the same thing also applies, again, as you can see, a drop, and here pretty much a dead heat between the 2 methods on the multi-was data set. So this is like a speech dialogue data set. So instead, what we decided to do is we decided to pre-train by injecting a compositional inductive bias in the joint representations of the textual and the tabular data to the language model. So in particular, we have our original annotated text to SQL examples, which we created in the previous data sets. We have 340,000 high quality databases from Wikipedia. And then we also created a large number of synthetic text to SQL examples, and we wanted to combine all this information to train the model in a better way. So we developed by hand a synchronous context-free grammar that takes into account the structure of the query. So you have values for tables and columns, and also different aggregate operators and nested queries and so on. And then each of those rules is built from some pair of input and output from the databases, and we replace all the terminal phrases with non-terminals so that we can have better generalization and be not domain dependent. Okay, so in order to do the pre-training, we ended up with 2 objective functions. One is column contextual semantics, that's CCS in this context here. And also we use something called turn contextual switch, or TCS. I'm going to explain how this works in a moment. So the input consists of questions, and then the matching tables. And then you transform each of those into a sequence. You encode them in the form of a sequence, and then use a BERT encoder in order to get the result. So pre-training GraPPa is done by pre-training Roberta or BERT in different experiments on the synthetic data using those SQL semantic prediction objectives. So the way that this works is that you give it as input the question, and then also the masked version of the sentence with the converted words. And then you compute this SQL semantic prediction loss on the Roberta output. Now, in addition to this objective function, we also use masked language modeling as an additional objective, and then we combine the 2 together to get better performance. So this is done both on the questions from the tables and also on the synthetic text to SQL examples. So we combine the loss, the masked language model loss, with the SQL semantic prediction. Okay, then we decided to evaluate this model on 4 different tasks. 2 of them on the left are fully supervised semantic parsing tasks. Those are Spider and WikiSQL. Again, WikiSQL is about single tables, and Spider is about multiple tables joined together. So by fully supervised, what that means is that we have the database itself, we have the natural language question, and we also have the SQL command that is used as output in the training set. Now, on the right-hand side in blue, you see the second settings, which is about the weakly supervised problem. So those are semantic parsing tasks on wiki table questions and wiki SQL, but in a different environment. In this case, we have a table, in this particular case, a single table, but we don't have the SQL code itself. We just have the answer. So we have to learn without the latent SQL query that would give us the answer. So this is very similar to many other semantic parsing papers from Percy Liang and many other people. Okay, so here's what the data sets look like. We have Spider, fully supervised wiki SQL, wiki table questions, weakly supervised wiki SQL. In each of those cases, you have either like annotations and the different questions and database sizes. So I'm going to show you some results here. First on the Spider dataset. So the Spider dataset, as you know, is one of ours, and people at that time, this is done mid-2020, we were able to compare with SOTA at the time. At that point in time, the best performance was using RAT-SQL. And as you can see, if you add the GraPPa model using the masked language model objective, we get a performance improvement of 1.4. And then if you add the two different objectives, then we get a bigger improvement in performance, about 3.7 to 4% on the test. Now, the next data set is fully supervised wiki SQL. So in fully supervised wiki SQL, again, we get, using both of those objectives, we get a performance improvement of 2 to 3%. But this is done on a relatively small number of training examples, just 10K. So not the entire data set. So this was done in order to show that we have a robust system that can be trained with fewer data points. We're also getting an improvement even on the full data set, but that one was not as large as the one with a smaller number of shots. Then the next data set that we evaluated on is called wiki table questions. And again, here we have a nice improvement in performance on the order of 8 percentage points for the combined pre-training objective. And also on the smaller data set, we also have some reasonable 3 to 4% improvement. Now, the third data set is weakly supervised SQL. And as you can see here, we have an even more substantial improvement with the two pre-training objectives. We get 6.58, 5.4 percentage improvement using Wang et al. 2019 as the baseline. So some interesting observations about GraPPa. So first about generalization. So GraPPa was not specifically trained on a corpus that is optimized for the Spider data distribution, but it is still able to perform well when it's trained on one of those, but tested on completely different data sets like wiki SQL and wiki table questions. And then in terms of pre-training, we were actually able to do this very fast compared to Tabert and Tapas, the models by Yin et al. And Herzig et al. Some of them were trained for 6 days on 100 GPUs and one on 32 TPUs, whereas in our case, we were only able to train GraPPa with 300,000 steps on 8 16 gigabyte NVIDIA GPUs. Okay. So now the next thing that I want to mention is some more recent work from NACO 2021. This is the so-called DART dataset. So this is about table to text generation. So just to remind you where we are in this process, we are trying to close the loop. We started with semantic parsing and then execution models that are trained on the contents of databases. Now we're going to the second half of this loop. This is the generation and summarization side. So one interesting slide that I got from Sasha Rush a few months ago is that on the generation side, there's a lot of interesting tasks that people work on. So on one end is a very abstractive, high conditional entropy generation model, for example, class conditional generation, the kind of things that you get from pre-trained language models like GPT-3. And then on the other side, you have something that is very source determined with low conditional entropy. So when you do translation, you want the output to be semantically equivalent to the input as much as possible. And then there's another step here in this continuum that is data to text, where we have an input that is very strictly specified. So you want to capture the contents of a table or maybe a semantic representation like AMR or something represented in the form of RDF triples on RDF tree. but you want the output to match as much as possible the content, to be faithful to this original. So this is part of the continuum where we have worked for this paper. So let's look at an example here. You have a table of cars and there are a few efficiencies. So those are different models like 2014 Chevy SParC, which has a fuel efficiency of 119 miles per gallon, again, higher in city, lower in highway, and so on and so forth. And now you want to be able to ask questions like this: which cars get more than 100 miles per gallon? Now, as we saw before, if you do text to SQL translation, you can just move this into a SQL statement like select name, year, and so on, which will, once executed on the table, is going to result in this table here that tells you that there are actually 4 cars that have this kind of mileage, and in particular, one of them that has the best mileage, which is this Nissan Leaf. Now, on the generation side, you may want to get the list of the cars that have more than 100 miles per gallon. That's very easy. You can just list them. But you also want to be able to generate sentences on the output so that the user doesn't have to look at tables, especially if the tables are very long, or if you have some sort of a spoken audio environment where showing tables may not be feasible. So in this particular case, we want to be able to take as input the row at the bottom, the 4th record, and to generate a grammatical sentence that is also faithful to the original input. In particular, we want to say that the 2013 Nissan Leaf electric vehicle gets 102 miles per gallon. So just like in the semantic parsing problem, some of the words here map to different columns, like for example, year, some map to values of the table, some map to the entire table, and some map to words that may not even be in the table itself. They may be in some description. For example, here, miles per gallon does not show up in the table itself, but it is in the metadata for the table, either in the title or in the description of the table. So when we started working on this, the total data set, which was published before our paper, was not available. So we started creating a data set from scratch. So this data set is called DART. And the way we did it is the following. We started with Wikitable questions and Wikitables in particular. And then we asked our human annotators, both internal annotators like students in the lab, but also a large number of crowdsourcing workers on Mechanical Turk. We ask them to perform the following task. We give them a table, and then we say, okay, say something interesting about this table and specify which cells of the table and possibly which parts of the metadata is used, or are used rather, to generate that sentence. So in this case, we have a table about football, like American-style football stadiums in Europe. And in this case, you have the middle record here that talks about a team based in the Netherlands who plays on Olympisch Stadion, and that stadium was opened in 1928. So we highlight those cells, and then we write a sentence that describes the content of those cells. So we found out that in addition to the data in the table itself, we also have to take into account the metadata. So like, for example, the title of the table, the column headers, and so on. But also more interestingly, we had to convert the entire metadata of the tables into a tree, so that we can see which attribute depends on which other attribute in a database sense. So for example, a city is a property of a team and a stadium is a property of a team. But capacity is a property of stadium and open is also a property of stadium. So we cannot directly associate capacity to team. So one of the things that we had to do was to convert those tables into a tree representation, again, that has a richer database inheritance structure and dependency structure. So once we have this, then we can extract triples. Those are what are called the RDF triples. So this is a standard semantic representation in the semantic web context. So we create triples that correspond to the content of the record that we want to summarize. And then we combine those triples into a tree, which is fully connected. So then I'm going to skip a few slides here, but we went to an extensive data collection stage. We went through some of the more domain-specific data sets, such as E2E and WikiSQL, which are two of the standard evaluation data sets for this kind of data-to-text problem. But again, they're fairly domain-specific. And then we also started from Wikitable questions, which is about very domain-independent examples. So we ended up collecting a data set that contains 82,000 what we call darts. So each dart is essentially a tree of RDF triples. I'm going to show you some examples of those. Here, so here's one dart. So this one has two triples. William Findlater or Findlater took office. This is the predicate in 1915, and this person's party was the Liberal Party. And then when you combine those two RDF triples into a RDF tree, you can get a sentence that describes the content of the entire tree. In this case, William Findlater, a liberal, took office in 1915. So this is a relatively small dart that has two triples, whereas we can go as high as 8 in many of the cases. So we have here an example with 6. And what is interesting to show here is that some of those triples refer to some of the metadata. So for example, in this case, we refer to the table context and also to the table title as metadata points. How much time do I have?
Yeah, 5 minutes.
Okay, thank you very much. Okay, so I'm going to go through a few more interesting projects that we have been working on. So the Dart data set again was published, but as usually happens, with some interesting projects, we were beaten by the total data set, which was larger than ours, but was developed in a very different way. So they were starting from existing sentences in Wikipedia pages that are near the tables, and then ask human annotators to simplify them and to clean them up, whereas we started completely from scratch. So we gave the annotators the tables without any context and asked them to write sentences from there. So this provides for an opportunity for evaluating future systems on two very different types of data sets, even though their format, data to text, is generally the same. Okay, so now I'm going to show you one other thing that we've been working on. So this is table summarization. This is an ongoing project. So one of the examples that I showed you earlier was about generating a sentence from a single record. Now what we want to do is to be able to generate a summary of the entire table. So for example, in this case, we want to say that 4 vehicles get more than 100 miles per gallon. Then possibly if you want the summary to be longer, you may also want to include the names or the models of the different cars that have this kind of mileage. Okay. So in order to do this, we again started creating a data set. Again, this is our specialty, creating large manually annotated data sets. So one of them starts again from Wikitable questions. And then we ask people to read each of those tables. We limited them to tables that have fewer than 15 records so that we can manage, from a cognitive point of view, the data set. And then ask people to write summary sentences for the entire table. So by summary sentences, we mean two different things. One is in the context of a specific user question, and the other one is in the context of no question, in which case we want to identify automatically either what is called in the database community insights, or to find something that is generally true about the entire table, not just about some separate part of it. Okay, so then once we have those summaries, we asked human annotators to go through all of those examples and to give us some score of the quality of the summary, how informative it is, how much it covers the most important points of the input, how grammatical it is, and so on. Okay, so I'm going to skip a few slides here, very quickly mention one other project. So this was a paper recently accepted by TACO. It may appear by the end of this year, more likely to appear in 2022. This is called the FETA QA dataset, and it's about free-form table question answering. So quickly, an example here is again a Wikipedia table, German submarine U-60 from 1939. Then you have a table, and then you have a region of the table that you want to refer to, and then a question that has to get a specific answer produced from this particular region. So here we have a question, a region, and then an answer, which is based on information from the table. So again, we have collected a large number of such data points. Right now we have a total of 10,000 tables, and you can see we have 7,000 questions for training and another 3,000, so total of 10,000 total training, dev, and test. Okay, so let me skip a couple of slides here and get to the final slide. So in this presentation, I tried to show you some recent work over the last 3 years in the Lilly lab at Yale on closing the loop in natural language interfaces to databases. We started first by creating a cleaned up large text-to-SQL data set. And then we moved on to dialogue datasets, to a language model for tables, generation from tables, and table-based question answering. And we're currently working on the summarization part, which hopefully will result in a paper in the near future. So those are some of the papers that I cited here. When I share my slides, you should be able to click on those links. And then I want to thank everybody for your attention. I in particular also want to thank the co-authors, starting with Tao Yu, again, the PhD student who finished recently. He moved since then to Hong Kong University as an assistant professor. His name is Tao Yu. And then all of our other collaborators. So our lab's URL is shown here. And I again want to thank everybody for your attention and for inviting me for this talk.
Thank you, Drago, for this wonderful talk. We have a couple of questions. Yeah.
Okay.
Yeah. Gautam, would you like to ask the question to the speaker?
Yeah, hi, Drago Gautam Shroff here. We met many years back in Yale.
I remember.
Yeah, so you talk about the accuracies. So, you said the exact match accuracy is around, say, 70%, and the execution accuracy was like 40%. But, I mean, it's a little confusing. If the exact matches are correct, then why would the execution suffer? Or is there something that I'm not understanding how this is computed?
Let me see if I understand the question. Is this the one you have on the screen, right?
No. At the very beginning in the Spider, the exact match accuracy on the SQL statement was around 70%, but the match for execution accuracy, that the values are correct or not, was like 40%. So why is there a gap?
I'm not sure I really understand the question. Do you mind if I answer it offline?
Okay, no problem. Yeah.
Yeah, sorry, thank you.
There is another question. T5 explores the limit of pretend models with 10 billion parameters, but soon the record was broken by GPT-3 model with 175 billion parameters, which has a good performance under the few shot or even zero shot setting. Afterwards, switched to Transformer, it proposed as the world's first trillion parameter pretend language model. Where this will end, what about common sense reasoning? All these datasets measure in English. What about other languages?
Okay, that is a really good question. Yeah, thank you. So multiple answers here. So first of all, there are now again trillion parameter language models which take months of GPU time to train, very expensive, obviously. So very few people can afford to build those. Now, in terms of common sense reasoning, I believe that the current models, as we know, GPT-3 has very interesting examples of instruction and, in their playground where you can write a very simple prompt like, here is a document that I just downloaded from the web, can you summarize it for my son who's 10 years old? And then with a very small number of examples like this, GPT-3 can actually do a fairly good performance. Now, one thing that I can see is that it works pretty well when the output is something simple, like, for example, classification decision, maybe up to translation, maybe up to summarization. But it doesn't really understand the common sense reasoning part. So we actually are working on a project right now where we have created a data set of what we call logical stories. Those are examples of sentences like Garfield is a cat, and then all cats have whiskers, and then you have questions like, does Garfield have whiskers? So we're currently working on this data set, and we have found out that the performance of models like GPT-3 is actually pretty bad. In some cases, they do surprisingly well, like, for example, if the example is completely self-contained. But once it starts referring to some outside knowledge from like the pre-trained model, then the performance drops to something like 50%, which is very, very, very low. And then the next question was about different languages. Yeah, so that is actually a very good point. I want to mention here briefly a project that is happening right now. I have a small role in it, so I'm not the right person to give you more details about it. It's called Big Science. you may have heard about. So Big Science was started by people at Hugging Face in New York, and it currently includes 700 participants from, I believe, 50 different countries. And one of the main goals of this project is to train, a really large language model that has two additional properties that some of the other language models don't have. So one is that will be highly multilingual eventually, and it also will be, it is actually being trained on data with clear provenance, like rights, and then there are provisions included in the model for removing, personal identifying information, for retraining, if certain pieces of data are found to be, compromised or tainted in some way. But again, the goal of that project and also many other projects that are happening, in major research labs is to go to a large number of languages, not just English. Now, in terms of minority languages, we're not there yet. I don't think that people are working very actively on this, but there are a lot of examples with few-shot learning for language transfer. And I believe in the future, this is going to become even more prominent.
Thank you. Professor Mukherjee, you can unmute yourself and ask.
Hi, Drago. So I was just wondering, in the first part of your talk, when you were discussing about extracting SQL queries from natural language text, so if I subset the problem to only scientific documents, so do you think that the problem becomes easier, or are there different challenges that would crop up? So what would be your take? Can one take up that as an independent problem and try to solve it? Would there be enough NLP and machine learning challenges out there?
I see. I agree that if you restrict your domain to be something that is a little bit cleaner text, so text that is more grammatical, which typically occurs in news, but also, as you mentioned, in scientific documents, then you should have an easier time, building a better model. But I don't know specifically how much training data you would be able to obtain in a domain like this, and also how well you should be able to transfer from one, let's say, one science to another. So if you have training data, let's say in the life sciences, does that mean that you get good performance in social sciences or in medical papers?
Okay, thank you. So these days, people typically submit the LaTeX files. Also, they submit the JSON files and things like that along with their main submission. So do you think that could come to some help, in generating the ground truth or the training data?
I see. Yeah, so I'm not particularly sure about JSON files, but as you probably know, there has been a lot of work, especially in the last year or so, on training pre-trained language models for code generation and for executable code in particular. So you have data sets that include, let's say, descriptions of problems, but also the code to solve them, and also the comments and the specs of the programming. So if you can train on both the code and the input text, so that usually results in some very interesting, systems like the, I forget what it's called. There's the Codex, but there's also this assistant for GitHub. I'm not sure, I forget the name of it, that was released very recently.
Thank you. Thank you very much.
Yeah, thank you very much.
Yeah. So one last question. Does the proposed techniques also apply to text to SParQL for graph databases?
Well, yeah, thank you. That's a very good question too. So we have not worked with SParC data sets yet, but we have been discussing them, and in particular looking at the graph representations of questions, in the form of those RDF trees. I believe that it should be very feasible to develop text to SParC using this kind of intermediate graph representation.
Thank you, Drago. Thank you very much. I would
Thank
like
you,
to.
Vidisha.
Yeah. I would like to thank again all the speakers and all the panelists and attendees.